So good morning, everyone. So today we start with an invited talk by William Cohen. He's a director of research and engineering at Google AI in Pittsburgh. He's a past president of the International Machine Learning Society and served as editor for the AI and Machine Learning series of books and for important international journals such as Machine Learning and Artificial Intelligence. He has a long-standing interest in statistical relational learning, the learnability of first-order logic representations, and in learning from data that has non-trivial structure. Today, his talk is about using deep learning platforms to perform inference over large knowledge bases. Thank you so much for coming, Ferrara.
Thank you so much for inviting me here. It's a beautiful city. It's great to be here. I always enjoy talking to this community. Let me get started. So in computer science generally, there's often a tension between elegance and complexity. So we'd like to have models that are as clean and simple and elegant and beautiful as we can. But we're also interested in modeling phenomena in the real world that is inherently complex. So if you look at biology, if you look at language, you look at the way people interact socially, these are all very complex things. There are a lot of moving parts. So if you want to model them accurately, you need a very complex model. At some level, the model has got to account for all that complexity. So there's two things you can do. You can spend a lot of time writing down a lot of rules. You can basically build sort of like an elaborate expert system, or you can have a lot of data that you feed into a learning system and have the learning system boil that large amount of data into a large complex model. This is the direction that machine learning has been going for many years, looking at learning from larger amounts of data, and the goal, of course, is to build models that describe complex, interesting things. However, where we've gone with this sometimes seems a little bit at odds with our goal of having things that are elegant. This is an XKCD comic, but I think it kind of is a little bit on the money. So we tend to be modeling everything we can with linear algebra, matrix tensor type operations. Sometimes they're quite elaborate. They're not necessarily all clearly motivated. And they're hard to understand, they're hard to debug. So that's a downside of the current approach to machine learning. Again, why are we doing this? Why did the world end up so that everybody's basically, essentially writing complicated models in MATLAB? So I'm not really sure. I think there are probably a lot of reasons why this is true. But one reason is certainly has to do with the hardware that we're working on. So, the first 40 years of my life, right? Every year the clock cycles for just your plain old ordinary desktop machine or your nice big server machine got faster and faster. So if you look at, if you look at these green lines right here, this is clock cycle. So that's like sort of like, the easiest way to make a machine faster is just to speed up the clock, right? So for many, many decades, the clock cycles got faster and faster. And then, something around 10 to 15 years ago, they started flattening out, all right? So it became much harder for machines to just naturally get faster. So what we needed to do in order to work on larger and larger models more quickly was look at parallelizing things, so using many, many more cores. And the extreme case of using many more cores, of course, you can get a machine now that has, 8 cores, 16 cores, 64 cores. So you can get machines that have that are parallel. But the machines that have the largest amount of parallelism are GPUs, graphic process units. So these are actually this is basically showing the time. This is, including parallelism, right? But this is the speed up for these guys. over the period from like the early 2000s to about 2013, 15. And sort of since then, I guess I got the number for 2017. So the Google tensor processing unit that was announced last year was about 10x more than that. So now they're about 2x further than that. So this curve is still increasing, all right? But there's a trade-off. What you have to do is you have to go parallel, okay? So you can't really work on a conventional sort of like single processor machine anymore. And there are really sort of two ways you can have a large amount of parallelism, right? So the largest amount of parallelism is on clusters that run Hadoop or Spark, and those are very good for certain types of things. They turn out not to be very good for machine learning algorithms, because machine learning algorithms, there's usually an iterative optimization step. You have to pass over the data many times, and that turns out to not be very efficient in that particular architecture. Or the other thing to do is use something like this. So this is a machine that's got a whole bunch of GPUs kind of stuck in here. And the thing that those are best for, honestly, is running a big pile of linear algebra. So that's kind of what we're doing and why we're doing it, you know, in my humble view. It's largely a question of what we can do computationally efficiently. And we need to make that, take advantage of those computational efficiencies to keep pushing the field forward. So, new title for my talk. So I'm going to talk about probabilistic logics that run on GPUs. So for this audience, I'm not going to try and motivate why I think a probabilistic logic is like an elegant, clean way of doing things. I hope you'll sort of like accept that as an axiom. And I'll talk about my work or my efforts over the last few years to basically make these sorts of computational systems friendly to GPUs and scalable on GPUs. So I guess I should also say, if you have questions throughout this talk, you know, just raise your hand and ask. It's a pretty small group. I don't mind being derailed. I also know that the acoustics in this are a little bit echoey. So if there's something I say and you just want me to clarify, then please let me know. Okay. So the system I've been working on is called TensorLog. And I'll just like start by giving you a few key ideas and a little bit of background. So it's a deductive database type system, a probabilistic deductive database. So on a deductive database system, it's a prolog, but you're limited to two types of definite clauses. You have unit clauses, so facts, unit ground clauses. And all the unit clauses have some measure of confidence associated with them. And then you have ordinary horn clause rules. Officially, the way the ordinary horn clause rules should be written is they shouldn't have any constants at all. So there are certain types of constants you can, you know, basically kind of work your way around. So for example, we have a constant tired, right? Which we could eliminate by having a special predicate, which is only true for the constant tired. The other thing which sort of seems like a restriction is it seems like a restriction that you're only allowed to weight facts and not rules, but that's also not really a restriction, because if I want to put a weight on a rule, what I can basically do is I can add some fact to that rule. I can add a literal to the body of that rule, which has a particular weight, and I'm sure that fact is only used from the database. That fact from the database is only used in this one rule. So essentially, this is basically assigning a weight to your confidence of that interval in your confidence for that type of inference. So this is really reasonably expressive. So I'm going to assume the parameters are weights for facts, but that's not a big restriction. I'm also going to make some other assumptions which are a little bit more stringent. So the predicates are either unary or binary. So that's a real restriction. The rules have no function symbols or constants. So this is something we know we actually can implement, you know, with, you know, soft logic. And, you know, we've heard actually a number of talks already in this conference about doing that. So there's a very natural way of doing this. right? So the basic idea is I take every database fact and I convert it to a neuron, okay? And I also need to do this for every possible fact that I could infer. So basically everything in the airbrand base of this program, I turn into a neuron, all right? And then I connect them up in a way where the neural, feed-forward network will do the same thing that the logical inference would do. Okay, but that's actually really too big. So even, something like this very simple little program, okay, I will need to look at inferences that include every possible pair of constants in the database. And if you have a large database, then that's going to be a lot of facts. So, just to kind of, calibrate it, if you have, a million facts in your database, or a million entities in your database, then you have 1 trillion possible facts. All right, so 1 trillion is a lot. 1 million isn't really that large for a database. If you're Facebook and you have, 2 billion, entities, 2 billion users, then n squared is really quite large. All right. So this isn't this explicit grounding stuff. It's a very elegant approach. There are lots of things you can do with it, but you can't use it for large knowledge graphs, at least not immediately. So what I'm doing in TensorLog is I'm using a different trick. So in TensorLog, whenever I'm reasoning, since all the predicates are binary, reasoning means answering a query like this one, right? So I'm going to find all the y for which p of a, y is true, okay? Where a is some input, okay? So a is an input and y is an output, all right? So this is the kind of reasoning you do. You pick some predicate, you pick some query entity, okay? You have a theory and a knowledge graph, and you find all the things that are related to a by that predicate. So what we're going to do, since we know the predicates all take this place, is we're going to basically turn these into functions. So the function is going to take a vector, capital A, which encodes the object A, or could, in general, encode a set of objects. All right, and the function returns another vector, which also encodes a set of things and confidences. Okay, so for every predicate and every mode for that predicate, we'll have a different function. So for each predicate P and the direction, whether we're going from input to output or backwards, for every predicate and for every mode, we'll have a different function. All right. So this is the basic idea. So these vectors will be size linear in the number of constants of some type, but that's a lot better than quadratic. So again, just to be specifically concrete, in general, when you're asking about a particular entity, so you're asking about, who's the uncle of X, X is the nephew, and X is a particular entity in the database you want to ask about, then X will be encoded with a so-called one-hot vector. So it's a vector, the length is the number of entities of that type. So here are the number of people. And there'll be a component for each possible entity, and it'll be set to be non-zero for just that one entity that is in the set. And at the end of the day, you'll get an answer. Okay, so the answer will be also a vector, and the non-zero entries will be the possible inferences. So the possible entities that are related to X, your input X in that particular way, and the weights will be your confidence in that prediction. Question? What about the? Oh, I'm sorry. It's like the echo in this room makes it really hard to hear. Yes. Oh, no. Yes. Okay, great question. So the question, do I allow negation? The answer is no. Okay. So this is data log, no negation, no negation is failure, no answer set programming. Sorry, I don't know how to do it yet. Okay. Good question though. Okay. Yeah. Yeah, so Nada's question is pointing out another limitation. So the length of the vector is the number of entities in the database. So the length of the vector will be linear in the number of entities in the database. You know, sometimes this can be sparse and sometimes you can exploit this, but not always for reasons I'll talk about in a little bit. So let me give you a little bit of idea of how these functions are constructed. It's not super complicated. This is not intended to give you enough details to actually go out and implement it, but just to give you an idea what the algorithm is. So what you do is you construct something called a factor graph. So for every variable in your logic program, so I've got like a one clause logic program here, and the variables are x, w, and y. So for every variable in your logic program, you have a random variable, and the random variable is associated with a distribution over entities. Okay. So this is a multinomial random variable, and those are coupled by these square nodes, which are called factors. So essentially, these factors are going to ensure that the distributions for x and w are compatible with the parent relation. So what does that actually mean in practice? So x and w have to be vectors that describe a set of objects, and the parent relation will just be a binary matrix in the case of facts with no confidence. It'll just be a matrix with 0 ones. It'll be size n squared, where n is the number of people, okay? But the number of non-zeros will just be the number of facts in the parent relation. So this will ensure that these two variables have the right relation, that parent of x and w is true, and that brother of x and w is true. There's an algorithm for manipulating factor graphs called belief propagation. And for something simple like this, where it's basically just a chain, what the belief propagation is essentially doing is you taking a vector for x, you multiply it by the matrix for parent, okay? Then you come up with the answer for that, and you multiply it by the matrix for brother, and then you end up with the output y. So in general, it can be a little bit more complicated. So if we've got a defined predicate in here, then you can't just multiply it by a matrix. Instead, you have to sort of like jump to another subgraph and do inference on that subgraph. So this lets you write recursive rules, right? Rules that can call each other. So you have sort of have a non-trivial program, but the graph has to be fixed size, so you can only go out to like some fixed depth. You can also have multiple rules for the same predicate. So if I've got, say, multiple rules for well, what am I doing here? Parent of your sister's parent or your uncle's spouse. So these are multiple rules for aunt. Then you can sort of copy the inputs in two different places and you collect them, and the way you collect them here is a sum. You can do relatively complex things. The general case is you basically load your evidence variables into this factor graph and you run belief propagation. And at the end of the day, what you get is you get something which I think is probably familiar to a lot of you. It's a weighted number of it's a weighted count of the proofs that support an inference. So the number associated with a particular constant c and y is the weighted count of the number of proofs that support, P of AC, where P is your predicate, A is your input, and C is the output. So this is almost an algorithm that I can run on a GPU. You could run this algorithm on a GPU, but we can actually do a little bit better. So belief propagation in general is an iterative algorithm. There's a convergence criterion. You have to decide when you're going to stop. So in a particular case where the clauses are polytree, which basically means there's one path of dependencies linking every free variable to the inputs, to the bound variables that are inputs. Then the belief propagation is just going to converge in linear time. They'll result in some fixed sequence of messages that are passed. All right, you can compute what that fixed sequence of messages is for that input, for that mode, up front. Okay, so you have this fixed sequence of messages. Every message corresponds to a very simple matrix operation, right? So I already told you can get vector matrix multiplication. You can also get multiplication of two vectors, which basically is sort of an intersection type operation, and. There are a few other ones that involve, like, for finding the norm of vectors, but there's only a small number of mathematical operations. So what you end up with is when you take a program, if I want to execute this uncle program, where this first thing is the input and this is the output, then I'll get this sequence of messages that need to be executed, okay? Or if I want to execute this one, then I'll get this fixed sequence of messages. All right, so this sequence of messages is in fact the right form. This is a function that takes an input and gives me an output vector. It's a fixed function, okay, so it's something I can pass to, a deep learning system like TensorFlow or PyTorch, whatever your favorite one is. And you can say, here's my function, I want you to optimize this and make this go as fast as possible and compile it for a GPU. So this is how TensorLog works. This is how it constructs these functions. And essentially each one of these functions is a type of proof counting function. So, so we had a comment about negation. We had a comment about the size of this thing. So the other thing that a lot of people don't like about this is this particular semantics. So the semantics kind of makes sense. It's a proof counting semantic. So the semantics depends on the particular syntax you use for your theory, okay? Another way of doing this is a model counting semantic. So, and arguably, so in proof counting, essentially what you do is for every answer, you find all the derivations that support that answer. There's a weight for each derivation, which is just the product of all the facts that were used in that derivation, all right? And then you sum up all those things to get the weights of the derivation. So this is an unnormalized stochastic logic program. So it's not anything new semantically. It kind of goes back to Jamie Cousins and Steve Muggleton's work back in, I would say, maybe 16, 17 years ago, something like that. The only thing that's new here is that you're computing the weights using this dynamic programming algorithm based on belief propagation. So that's nice. There's cases where you could have many derivations, exponentially many derivations. You can get an answer efficiently. The other way of defining semantics for a probabilistic language, which is more common, is model counting. So what do these confidences mean? So in this setting, it's not really clear what they mean. If you were going to assign a meaning to them, one natural thing to do is say, well, that's the probability that that fact is true. So more specifically, what I'm going to do is I have a distribution over ground databases, right? And the way a dead ground database is constructed is I draw each fact with probability dependent on its confidence. So if the confidence is 0.9, then in 90% of the databases I construct, that fact will be included, and 10% it won't be. So then you can look at running your normal inferences on top of this randomly chosen database, and the probability of a derivation, a derived fact, is just the probability that a randomly chosen database will imply that fact with a theory. So this is the way ProbLog is defined. There are a bunch of other probabilistic databases that are defined this way, and this is not the semantics I'm using. It's much heavier computationally to do this. Okay. So now learning. So if you're interested in how learning works in TensorLog, then wake up now, because this is the whole slot. This is everything I'm going to say about learning. Okay. Do not go downstairs and get an espresso, and then come back for the interesting part, because you'll miss it. Okay. So we have a numeric function, okay, that does our proof counting. So for learning, what I do is I'll define a loss function. So by default, the loss function, I'm basically going to take the output, which is the proof counts. I'll normalize it in the neural network way, which is by doing something called the softmax. All right. Then I will compute a loss function based on some target value. So that loss function basically now tells you how close you are to the desired output. So you just minimize that loss with gradient descent. All right. So gradient descent basically means you can choose any of the inputs to this function. They're all differentiable, right? We can choose any of these inputs to the function, to this function, and vary their values. So what I'm going to do is I'm going to vary the values of the underlying confidences of the facts. So there's not a whole lot more to it than that. I mean, there's a little bit of twiddles because I want to keep the facts positive, though confidence is positive. So there's some reparameterization, but it's basically all that's happening. So learning is basically free. So in the way I'm going to do this, I'm going to compile to something like TensorFlow. TensorFlow has got optimizers that have been sort of carefully tuned and optimized. It's architected to do this kind of gradient descent operation, so it's architected to evaluate these functions iteratively, compute their gradients efficiently, and update their gradients. And that's basically all I need to do for the learning. So the learning is very simple given this architecture. Steve? Yes, right. So this is parameter learning, not structure learning. I will talk about structure learning in a couple of minutes. Okay. So there's actually 2 implementations of this that I'll talk about. So for this to be effective, one thing that must be true is it must be true the matrices that correspond to the relations have to be sparse, right? Otherwise they're n squared and the whole thing is like pointless. So you have to use sparse matrices. So it's nice if you can also use sparsity for the sets of entities that are involved as well. So there are 2 implementations. One allows sparsity for both entities and facts, but it's basically kind of like a TensorFlow-like system that I wrote myself. So it's kind of a homegrown version. And then there's one that compiles to the actual TensorFlow neural network implementation. And the downside of that is it doesn't do everything sparse. So there is not, as far as I know now, a native CUDA sparse matrix multiplication. There are reasons why that's actually very hard to do efficiently. So in TensorFlow, you basically have dense vectors of entities. So you have dense sets of entities, and you have sparse relation matrices. So I'll say a little bit about how this works. So here's one kind of sample task. So this is question answering. So we're going to start off with a question like this one. You know, what's a film written by Luke Rickey? Answer is How to Be a Serial Killer, or who acted in this movie, and there's a list of actors' names. So there's a knowledge base. So there are 2 problems here: looking up the answer in the knowledge base, all right, and also figuring out how to do that knowledge base lookup by looking at the question, all right. So this is, you know, one of these problems that's been kind of kicking around the neural network community for a while. The way I implemented this in TensorLog is the following. So this basically says the answer to a question is an entity if, let's say, the question mentions a movie, okay, and that movie is related to the entity in the appropriate way. So here we asked about who acted in the movie. So, you know, what actors were starred in this movie? So that's the right answer for this type of question. And then you also have to figure out what type of question it is, right? So here's another type of question. There are several different relations here, so there's a bunch of different questions. There's a rule for each one. And there's this little additional code here in each rule, which you can think of as a linear classifier. So basically, you're taking features of the question, which are, in this case, are just the words in the question, and then there's some learned weight for each feature. Okay, so to the extent that this question has words which have high weights, and the weights here are starred actor weights where the mode is IO, right? So this is the type of lookup you want to do in the database. To the extent that that's true, then this should have like high counts, all right? So this is, you know, another set of weights that say this is a written by question, all right? So this is the model that you write, and here's some numbers for training. So this is you know, a database with a little bit more than 1 million facts, 500,000 about the movie, but then I've also kind of put features of the question and, you know, what entities are mentioned in the question into into the knowledge base as well, so that it gets a little bit bigger. So these are some numbers. This is very fast for a probabilistic programming system, although not particularly fast for a neural network system. And it does pretty well. This is, slightly better than the previous state of the art. Since I've been talking about this, some people have gotten up to like 96, 97, but it's pretty good. You could also extend this pretty easily. So I haven't done this yet, but we could also take this theory here, right? So this is basically the same, classification is, telling you whether this is the right relationship to use, okay? And now mentions entity is actually not a database thing, so it's not something I'm going to pre-compute, but it's something that I'll write a rule for. So you could say, the entity is mentioned in the question. If there's some n-gram that matches the entity, right? And this is so here. This is basically sort of like a match, and I want to say the entity is a popular entity, okay? And then matches, basically, you could just say, 2 n-grams match if they share a common word. That's an word. So here, popular for the entity and important for the word would again be learned predicates. So you could do something like this. I haven't done it, but I'm pretty sure it should work. So here are some other experiments. A couple of years ago, I talked about a different learning system called Proper, which I also was arguing was very scalable. So this is kind of roughly showing that if I do parameter tuning in TensorLog, I get results that are not typically worse than they are with Proper. They're generally pretty comparable. And here's some more scalability experiments. So before I showed you experiments with about 1 million facts, the inferences were also fairly simple. So they weren't long chains of inferences. So in some of Luc Derate's Problog papers, he's posed a very simple kind of reproducible transitive closure task on a grid. So his experiments were on a 16 by 16 grid. I basically took that and sort of ramped up the size of the grid. So a 200 by 200 grid has like 40,000 entities, about 350,000 facts. And we're going to do deep inferences. So these are inferences that are maybe 10 or 12 levels deep. So this is very large databases, shallow inferences. These are somewhat smaller databases, but larger inferences. And the grid task is basically just this, right? So the grid task is you have entities that are named for cells of the grid, and you have facts that are the connections between each grid. So we're going to start out and weight everything uniformly, and the program is just a transitive closure program. And the learning tasks are a little bit different, but the most common one is it's sort of a navigational task. So what I'm going to do is I'm going to put a landmark node every, say, 10 cells. So every grid of 100 cells will have, every subgrid of 100 cells will have one landmark node. And the goal is to weight these edges so that when you ask for something transitively connected to a node X, the thing that's highest scored will be the nearest landmark node. So that's the basic kind of task that I'm looking at. So first, let's look at the inference times. So this is Proper, okay? And this is looking at larger and larger things. So this is queries per second. So of course, it's getting slower as things get larger, okay? This is kind of the homegrown implementation. So it's generally not faster than Proper. So the italics mean that Proper is the fastest system. But there are also some things you can do to speed it up. So in neural networks, one way you speed things up is you group examples into what's called a mini batch. So you'll basically do the inference for a set of maybe 10 or 25 or 100 examples at a go. And you can do them in parallel all on the same GPU. So this is putting 25 things in a mini batch. This is putting 250 things in a mini batch. Okay, so now we're actually going a little bit faster than Proper on the shallow tasks and some of the deeper tasks, but it's not a dramatic change. If we look at sort of like Google's implementation, we get we get these numbers, and if we look at sort of taking that and moving into a GPU, then finally we're sort of starting to see cases where the inference is faster. Okay, so some of these numbers there's a large speed up, but in many cases it's actually kind of like disappointing. So it's maybe 1.5 or 2 times faster than the kind of basic CPU-based model. So why aren't we getting these speeds? Well, the reason we're not getting these speeds is because these systems are architected for repeated operations, right? So the idea is we want to load the functions into the GPU and run them through the same data over and over and over again. So if we start looking at learning, we see some pretty different numbers. So this is the time it takes to learn with the SciPy implementation on these grids. Okay, so it's not terrible. Okay, but if we look at TensorFlow on GPUs, it's much faster. So so this is roughly 500 times faster than sort of my simple homegrown implementation, and there's again maybe like a 10x speed up over the CPU implementation. I think in the interest of time, I'm just going to skip over this, and I'll talk about a few other extensions, other experiments I've done. So I described one loss function. So this is kind of a funny loss function. What you're doing is you're taking the outputs and you're normalizing them. Okay, so given a particular input, the outputs, the confidences of all the outputs should sum to 1. And in some cases that's what you want, but in many cases it's not what you want. So if I'm basically ranking people by their confidence in being Bob's uncle, it would be useful maybe if I got the people that are actually Bob's uncle ranked higher, and maybe that's all I really care about. But in other cases, I might want to know the difference between these two people with high confidence are Bob's uncle versus, there's one, I know he has one uncle and I'm not sure which of these 2 people it is. So this is a convenient function to optimize, but it may not be the semantics you want. So you can do something different. So instead of basically doing this softmax normalization, you could basically instead say, well, I've got these proof counts and I'm basically going to use these as inputs to another little neural network. So I'll just basically run these through a logistic regression with a bias. So now these can be pushed to either 0 or 1, depending on the value of this bias term and the proof counts. The loss function is still cross entropy. So all I've really done is I've sort of added a little bit of neural network on top of the inference, the proof counting inference. Learning is still the same. What I did was I used this to basically try and match the semantics of Problog 2 on this grid task. All right. So essentially what I did was I estimated Problog 2's probability scores by just using a sample of like 1 million knowledge graphs for the grid. And then I ran learning. So this is the difference in probabilities between these 2 models before training. So the fact that these are all red means that things are really quite different. No, I'm sorry, these are just the probabilities. So what I have here is every pixel is corresponds to a pair of points on the grid. So there's 100 pixels down here and 100 pixels across here because it's a 10 by 10 grid, and it's just scaled differently because that's the way this graphics package likes to draw it. So so this is the probabilities of the transitive closure before learning in TensorLog, and this is the probabilities of the transitive closure in the tuple independent model. Very, very different. Okay. This is after training, so you can see after training it's getting a lot better. The error is dropping by a fair bit. Here's another visualization. So this is the difference in error probabilities before and after training. So so this is basically showing that you can use this to learn kind of a different semantics. Here's another thing that you can do, which again is like something that's kind of one of neural networks. So rather than having a fact for every edge relation, I could define those things in terms of some latent representation for the entities. All right. So instead of basically just having confidence of 0.2 that's associated with this pair of entities that gets tuned up and down. What I'll do is I'll construct a latent representation for each entity, and I'll write a function that computes that confidence. Okay, so the function is something like this, which isn't particularly important. But again, this is just sort of a verification that you can do this. So now we basically put sort of a little neural function underneath the inference. So what was a database predicate is now defined by a neural model. All right, and we're still getting a very nice kind of learning behavior. So I want to take just a couple of minutes now and talk about the structure learning extension. So this is somewhat preliminary work. If you recall, the way a TensorLog program works is it's compiled to a sequence of operators that are then performed in a fixed sequence. All right, and each operator basically does something. It takes one or two memory locations, and those memory locations often, but not always, correspond to a logical variable. Then you take those inputs and you perform some numeric computation and you write it out to a new temp variable. Okay, so what we're going to do is, rather than use a fixed sequence of these things, what we're going to do is I'm going to learn a neural controller for this sequence. So I've got basically a set of memory cells. I've got a set of operators. Okay, at each step there's going to be this like soft neural controller. So it's going to put a weighting over the different operators and a weighting over previously used memory cells. Okay, and then it's essentially going to compute a mixture of all the operators over all the inputs according to that weighting. Then it's going to output that result of that mixture into a new memory cell. So in principle, this can learn any operator sequence you like. So in practice, it does a pretty good job at a lot of structure learning type problems. So this is the Wikimovies task. Again, it's using natural language queries, so the controller can be governed by any sort of initial input. So you could give it an initial input, which is just the name of the predicate uncle and the starting point, if you want to do kind of a traditional ILP task, or you could give it something that has, you know, another neural representation, like say a natural language query. So this is on a couple of statistical relational learning tasks. This is on the Wikimovies data, and it tends to be pretty competitive. It actually performed much better on these tasks than proper using the iterative structural gradient descent method. And I guess these are on some knowledge-based completion tasks. So I'm going to skip over that a little bit in this. And I'm going to just spend maybe 5 minutes, just we have some time for questions. I'll spend maybe 5 minutes talking a little about what I'm doing next. So this is now speaking as William Cohen from Google. I've been there 3 months. And it would be really interesting, I think, to get this sort of technology more widely used, embedded in Google, and used for some interesting things. But I think there's some difficulties. So this is the model that we have for like the movie case. So this is a relatively simple model. But there's still a lot of stuff that's happening under the hood. So this thing is going to get compiled by belief propagation into a sequence of operations. As a programmer, I don't know what that sequence of operations is. It's a little bit hard to predict. As a programmer, I don't necessarily have as much control over the process as I'd like to have. It's also using a declarative programming style, which it's not that familiar to a lot of people that are programmers at Google. Even if they did know it, it's not that well suited to integrating to this kind of pile of linear algebra models that might be combined with it one way or another. So how can you make this into something that's more easy, that's easier to combine with kind of existing neural platforms? So we'd like to be able to predict what we're doing. We'd like to swap back and forth between TensorFlow and TensorLog type operations. Another thing we'd like to be able to do, which is kind of awkward to do in TensorLog, is to quantify over relations. So there's no second order reasoning in TensorLog, but for questions like this, I mean, really, having a rule for every relation in the knowledge graph is a little bit awkward. Really, I'd like to say just what relation should I use? So you'd like to do some sort of second order reasoning here. So the idea I've been looking at recently is writing a query language which corresponds one-to-one with the language that TensorLog gets compiled into. So now I know that you can express everything you could express in TensorLog because you're expressing the full sort of back-end language, but you're no longer asking the system to do this like complex compilation step. So here's some very quick examples of this. So this is going to like my Wikimovies case. So before I said something like I want a movie that's mentioned in the question, and I want to look at the starred entities, the actors that starred in that movie, and this is all controlled by the features in the question, right? And whether those features, here's the slightly different way of writing it, whether those features indicate the starred actors relationship, okay? So basically, I'm going to start off here. I'm going to basically say I'm going to look at the question. I'll take the entities that are mentioned. Then I'll take the actors that starred in that mentioned movie. All right, and this whole thing is gated. So that is true if this set is non-empty. So what is this set? Well, there's some feature of the question. All right, and it's also one of the features that indicates starred actors. So one just basically is generating a constant here, okay, and indicates means I'm basically going backwards. So this is the features that indicate starred answers. So this is a different way of writing that, this answer question using a more kind of like database query type language. It's kind of interesting. There's actually a very small number of operations you need to get everything that's in the target language for TensorLog. It's also possible in the design I've prototyped to do second order reasoning. So if I want to quantify over relations, the trick is basically I just reify them. So I take this tuple, which basically said a fact which said, Tom Hanks starred in the movie called The Post. All right, I turn it into 3 tuples, right, which are all talking about a particular fact, T37. It tells you what the relation subject and object, or verb subject object are of that. Okay, and now I can write this construct. So this says if G is a set of relations, then I'm going to follow G by basically finding a tuple that has X as the subject, okay, and it has G as the verb, okay, and I'm going to take the of those tuples. So this is basically just design. This is just the in the other query language, but of using the sort of reified representation. So this is basically what I had to say. So right now we're kind of trying to build complex models in a way which essentially ignores, I believe, some of the elegant and powerful techniques that we've developed over the years. And one of the big questions, I think, is how you can integrate techniques like logic and logic programming with the kind of hardware we need to use for modern large-scale learning problems. So this is one particular answer. And as people pointed out, there are a bunch of different trade-offs. So it's a scalable approach, but it's also a very restricted subset of Prolog. It is combinable with neural methods, but I don't know. I think there's probably a lot of work that could be done in architecting other language subsets or looking at other ways of combining these different approaches. So this is one approach at looking at this problem, but I think there are many, many others. So I'll stop here and take questions.
So the random variables are the individual, not the atoms.
Yes, the The random variables, so this is a weird way of doing it. The random variables are not binary variables that indicate whether an atom is true or false, whether something in the airborne base are true or false. So almost every other probabilistic logic works that way, okay? Instead, the random variables are multinomials, so they have a huge domain. Their domain is like all the constants in the database. And they're coupled by these, so they correspond to variables in the proof.
So when you derive conclusion, you get the probability distribution of the input. The answer.
Yes. Yeah. Exactly. Not a.
Your representation is a deductive database.
Yes.
But I think you could get the speed up in case you would have type variables, because then the metrics.
Yeah. So the question is about type variables, and that's absolutely right. So the types are really important, right? So the numbers I showed you, like for the wiki movies, there's at least a simple typing system. You want to keep the words in the language different from so the feature is basically different from the facts in the database. So it actually is really important to have typing sort of from a practical point of view. For a lot of cases, what you care about at the end of the day is like a classification decision, and that's over a small set of things rather than a large set of features. So yeah, TensorLog is typed, and the neural query language is typed. There's a simple typing system underneath it. So the typing is very primitive. It's basically, essentially you're putting the entities in each type in a different space, right? But they can, share the same vector indices. Yes, Steve.
So the early class we were talking about probabilistic logic programs and programs, and then we had Neural ILP, but you couldn't quite describe what's the relationship between the neural part is and the probabilistic programs. I mean, are the weights for the neural network equating to probabilities, or?
So is this for this guy here? This is what I call neural logic programming. Yeah. No, it's really all linear algebra, right? I mean, there's no neurons. I mean, it's what it is it's a controller, which is an LSTM, a recurrent neural network, okay? And what the controller does is it runs iteratively, and in each step, it outputs two vectors which are treated as control operations. So one basically tells you what operation to use, right? And the operations are, let's say, just like these matrix multiplication operations. So it tells you what relation to use next in your relational chain, if that's what you're doing, okay? And then it also tells you what the input to that relational chain is, okay? So what you end up with is a pile of linear algebra that just happens to do what a logic program could have done, all right? All right, so the parameters of that program, the parameters of that LSTM, the control parameters of that, those are the things which choose the sequence of operations. Now, you can, and I didn't talk about this at all, you can go and you can trace through on a particular input. You can take an input and say, well, which operations would have been performed, okay? And based on you can look at sort of the operations that have high weight in the neural controller, and you can say, well, based on this sequence of operations, what logic program would have compiled to these operations? So you can go back and get something which looks a little bit like a logic program. So you do have some explanatory power. But the fundamental thing you're learning is sort of, this fully continuous approximation to the discrete choice of steps that you would be using.
Yes. So you motivated this research by the use of GPUs as a massively parallel approach to computation. There are some other approaches that are massively parallel, such as Would they be more appropriate for machine learning, you think?
Yeah, so I don't know. There are certainly a lot of, how do I want to say this? The process of like sort of like doing kind of like normal, kind of like bottom-up deductive database inference looks a lot more like a message passing architecture that you might use, you know, something like Pregel or you know, GraphX or something like that. So it looks a lot more like something that you would do with a cluster machine where you're iteratively passing messages and sending information around and doing something like local inference. And I think that's another kind of interesting approach. So those sorts of systems tend to be, I would say probably like 5 years ago, it wasn't clear which direction people were going to go in the machine learning, whether they were going to try and do, you know, streaming operations through these, you know, GPUs, which can do parallelism, a lot of parallelism, but they can only look at a little bit of data at a time, right? I mean, they only hold like a few gigabytes of data. Or whether people were going to look at sort of like cluster parallel architectures. And people do use both of these things. But in this talk, I'm really focusing on the GPU parallel streaming type architecture, which is what, you know, I would say, you know, like 95% of the work over the last few years has done. It's not obvious that that's sort of the long-term best architecture for this. So I think there's probably room for looking at both different types, different approaches. I mean, this has a fundamental limitation. If you have a database that's too big to fit in your GPU, then you're let's see, what's the word? Screwed. It's because it sort of assumes all the database can be stored as sparse matrices.
So maybe I'm wrong, but I think that you can also combine really databases as much as you and then you look for related to the complexity of the query. So I think that really it's really for me that what we really is okay depends on the organization of the database. So for instance, if you have a lot of tables, you need the joint operation. So it gives a complexity related to the logical inference. And you can choose to make like a positionalization, compute the joint, make a view, etc. So I think that, for instance, if you are only one table from the start actor, if you have the name, it's okay. If you are only the key and you must find the name in another table, the method, even the semantic, that will be okay, we can be different. So the study of the database and the change of the representation can be very efficient even for the normal approach.
Yeah, so I think the answer to this is like pretty long, right? You know, the choice of what database operations I did was basically informed by computational complexity results. So there's some things that you could add to this that wouldn't change things very much. But if you add like three-place predicates, right, then things get computationally quite different. So the main issue is basically, you know, I could have like, you know, a single input and two outputs, okay? And if I'm only letting you output like, you know, as your output is like vectors, right? So all you can say is, here's the distribution over entities in the database, right? Then you can't express. And with that language, you can't express pairs of objects that have some sort of like, you know, interesting correlation, okay? You need some sort of matrix to do that, okay? So so that's sort of like a fundamental issue, and it is actually reflected. I mean, so there are things you can do with like so you can do, like, for example, you can do any polynomial circuit in one clause if you have 3 place predicates in your database. And you can't do that if you just have like binary predicates. So there are actually like some sort of like real restrictions, like computational restrictions that going to binary predicates has. But mostly it just, you know, this is something that's, you know, a lot of people use knowledge graphs. It's not like sort of an uncommon restriction, and it's much simpler in this setting. So I think there are things you can do, but I think it's a complicated future work sort of problem.
We have